Hi everyone, welcome to lecture 3. This is going to be covering projections, datums, and geodesy. We're going to do a quick review of some coordinate systems. We're going to look at what geodesy is and projections, the most popular ones, some general knowledge, and reprojections of original projections. We'll also look at geoids and ellipsoids and datums. So some familiar words here from lecture 2, we'll just go a little further into them. So just a few slides kind of reviewing some of the coordinates we've already discussed, such as Cartesian coordinates. You have your two-dimensional version, which is just going to be an x and y axis and a point on that axis, or more so on that figure. And then we have three-dimensional, which just adds in that z-plane. Latitude and longitude. Lines of latitudes are called parallels. Lines of longitude are called meridians. And the prime meridian is a line at 0 degrees longitude that passes through Greenwich, England. Together, lines of latitude and longitude give us a grid of the Earth. Another way that we can look at the Earth in a somewhat gridded format is through angles. So angular measurements look at latitude and longitude as well, but they're based off of the center of the Earth. So you'll see over here we have 60 degrees of longitude. We have about 55.3 degrees of latitude. I won't say that you really need to have too much of an emphasis on your coordinates. You just need to know what type of coordinate system you're using, whether it's angular, whether it is Cartesian. Once you're aware of that, you could play with the data accordingly. But you don't need to really memorize, you just need to understand that there are different types, and you may need to handle that data depending on the type of coordinates you're utilizing. The prime meridian passes through this point, 0, 0, the prime meridian and the equator. It's kind of right off of the western part of Africa in this projection. If you put data into ArcGIS Pro, so let's say that you have added a data layer or hit the Add Data button, you see it in your contents pane, but you're not seeing it on your map in the location it's supposed to be, check this point. Check 0, 0. There is sometimes an issue that occurs where either the projection is very off or there isn't a georeferencing that's happened. You'll learn about that a little bit later on. If that's the case, sometimes data will end up at 0, 0. You'll either need to kind of drag it back and then georeference it to the location it's supposed to be at, or you may just need to look at how you uploaded that data, if it even had any sort of geographic system placed in there in the first place. So, point of this slide, if you upload data and you don't see it where it's supposed to be, check out these coordinates. This right here is just showing you, again, kind of your prime meridian and your equator. It's also showing you some of the countries that fall between the equator and the Tropic of Cancer and Capricorn. So this is just one projection, again, of the world map as we've seen it before, and just kind of showing you that you have those main lines around longitude, or I guess latitude, excuse me. You have 23.5 degrees north and 23.5 degrees south. You probably learned this in a introductory course back in grade school, middle school, high school, but these are just areas to know. This relates back for you environmental people on where different climates occur typically. So I won't go too far into that for the sake of time on these, but just some information to generally keep in the back of your head. And as I mentioned, I'm going to be kind of flying through some of these slides because these are more of a sit and stare. Some of them are a little bit wordier. So you can pause on slides like this one. I won't go too far into it, but this kind of explains to you how these geographic coordinates are similar to using time in cases of degrees and hours. So again, if you're interested in this, you can come back to this slide and just pause on it. So when we identify locations, we have, again, our Cartesian coordinates, our geographic coordinates. Cartesian coordinates kind of work off of an XY type of figure, whereas the geographic coordinates kind of more so utilize angles. We're used to seeing geographic coordinates when you think of latitude and longitude, it's a geographic coordinate. When you think of X and Y points or even Z points, that's going to be your Cartesian coordinates. For Cartesian coordinates, that origin is always 0, 0, right here. For geographic coordinates, that origin is 0, 0, such as a few slides back where we saw that point off the western aspect of Africa. So when you use geographic coordinates, they can handle 3D surfaces pretty well because they utilize those angles. Cartesian coordinates are better suited for 2D surfaces. Again, we can throw in that z-axis, but between these two options, Cartesian coordinates are typically applied for 2D surfaces. They're better used there. Geographic coordinates are typically better applied for 3D surfaces. So some key terms we're about to go over: ellipsoids, geoids, datums, projections, and coordinate systems. These all kind of rely on one another, which is why you see this figure kind of stacked with that coordinate system as the base, the projection as the kind of next step up from that base, and then datums and geoids relying on what projection you're utilizing, and finally, that ellipsoid. So geoids and ellipsoids allow us to kind of capture the shape of the Earth. We'll go into what the shape of the Earth is, what we think it is. Datums have to help us to reconcile surveys. So when you may say that something is at point xy, when in reality it's actually at x1, y2. Projections help to make maps flat. If you remember from our very first lecture talking about that orange peel idea, if you take an orange peel or something that's spherical and you try to flatten it out, there's always going to be some sort of distortion, some sort of tear or yeah, basically distortion in that, going from a three-dimensional to a two-dimensional object. And then coordinate systems put everything together. Geodesy itself is the science of measuring the Earth, and specifically measuring both the shape and the size of the Earth. It helps us to understand, well, how big is the Earth? What is the shape of the Earth? Where is XYZ on the Earth in relation to other things? So, big topic that we hear all the time, whether jokingly or not, is the Earth round? There are a lot of different theories on what the shape of the Earth is. Some people think that it is flat like a pizza. Some people think it's more like a snow globe, where it's flat, but the atmosphere sits above it just on one end of it. In reality, no, it's not flat, but it's also not spherical. It's not this perfect circle that we think of when we think of the Earth and typical planets. It is actually called an oblate spheroid. And let's go ahead and click through these. So, an oblate spheroid means that this is bigger around the equator than it is around the poles. So, instead of being a circle like this, it's kind of more squished like that. And a lot of this is just due to the rotation of the Earth. You'll see over here that, and we've heard about maybe like the shortest baseball game ever played on Earth, where somebody was over near North America, the North Pole, and running around that North Pole takes far less time than running around the equator, which is the widest point. Logically, that makes sense, but when you apply it to the actual shape of the Earth, it also makes sense that it would be wider in the middle because of this too, because we're spinning, and as you spin, mass kind of pulls in the direction that gravity is spinning with it. We won't get into it, this isn't a physics course, but just to think about. This is an idea of what our Earth actually looks like, an oblate spheroid. So you can see that center is much wider. There's also some points that have higher elevations and lower elevations. When we compare just that north-south to the east-west aspect, you can very clearly see that it's not an insane difference, but there is a difference between that length versus that width. So for our geoid here, a surface where gravity is equal to exactly one gravitational unit, that's what we kind of refer to as a geoid. It's a measured surface, it's not mathematically defined, and it's measured by Earth-based and satellite-based instruments. It also helps us to approximate mean sea level. This here is not surface topography, this image that you see, but it's more so gravitational pull. And you can see some areas that we know are higher, such as over here. Other aspects as well, they have just a bit more gravitational pull on them, whereas some of our lower sitting areas that are here in blue have much less gravitational pull. So, Earth's shape is best described as a geoid. Again, we discussed it being an oblate spheroid, but we can describe it as a geoid because of all these assumptions that aren't mathematically based, but more so based off of on-ground measurements and satellite measurements. However, there needs to be some sort of math involved, right? We love to throw math into everything. So, because there is no math right directly associated with it, we can't depend on using, or let me recorrect what I'm saying here. There is no math just directly associated with calling this a geoid. And we can't use huge numbers and complex data to go ahead and form this calculation for us. We can, we're not interested in that though. So I hate how I structured these slides. I'm going to apologize. It's a little jumpy, but there's another thing called an ellipsoid. You can think of an ellipsoid kind of as that oblate spheroid in the sense that it's wider than it is tall. They are perfect mathematical models, but they don't fit the shape of the Earth exactly. You could ignore the function that we have up here. So Earth isn't an ellipsoid due to those differences in the gravitational pull we discussed a few slides back. This here is an exaggerated view, so don't freak out. It doesn't look this obtuse. So some different ellipsoids that we can look at and try to see how they best fit Earth, maybe certain sections of Earth. We have our geoids, we have our ellipsoids. We have ellipsoid A over here with this white shading and ellipsoid B. And let me go ahead and take us back here. Ellipsoid A and ellipsoid B, although we see this geoid over here, right, which is trying to kind of represent what Earth looks like in terms of its width and the differences around it, some areas will better fit ellipsoid A, some areas will better fit to ellipsoid B. So if you're on the eastern part of the world in this 2D projection, ellipsoid A is going to miss out on some areas, and ellipsoid B is as well. Whereas over here on the eastern side, you see that ellipsoid A, which kind of has this yellow line that comes in over here, is going to miss a decent chunk, where ellipsoid B may cover just a bit more. Origins for both of these, R1 and R2, of that ellipsoid are specified so that the separation between the ellipsoid and the geoid is as small as possible. Ellipsoids in this case have names. When we look at our projections, you'll see Clark, Airy, and Bessel. Keep this in mind. We also have global ellipsoids. These are for when you are looking at large expanses of land. Maybe we're looking at more than just one country. Maybe we're looking at an entire continent, for example. These typically have non-human names, WGS 84, ITRF 2000. You will see WGS 84 come up a lot. A lot of the times when we use global projections, global datums as well, you will see that this is utilized. This over here is chatting about datums. So it tells you a datum is the mathematical model of the Earth that we use to calculate coordinates. There are local datums, there's also world-based datums. WGS that we just mentioned here, this is the World Geodetic System. And as of back in the days, I think we have a new World Geodetic System now as of a few years ago. But as of, let's give it 5 years ago, we are still using that 1984 version as our kind of standard for a world-based geodetic system, or a world-based ellipsoid in a case. So datums are very important because, again, they tell us where things are on Earth, not just based off of maybe this projection or that projection, but it can take projections and then it can pinpoint where locations are between them. Let's say you're using this projection, your datum has to match. You can't use a datum that doesn't associate with that certain projection. So it's just kind of another layer of metadata, you can think of it like this, that really allows us to be precise in locations. And the reason that you see this in a case of like a tank in the background and some soldiers is when you provide a set of coordinates, they need to be specific in some cases. They really need to be specific. If you tell somebody that you're at point XY, but they don't have the proper datum to tell you where XY is, it could be a couple of meters off. It could possibly even be a couple of hundred of meters off. So it is very important that we know our datums, we know our projections, and we know that they mesh well. So we can agree on a best set of measurements that allow us to do surveys that are mutually compatible between the two. We typically agree that this marker is at 32 degrees latitude and negative 75 degrees longitude for datums. One bullet point that I want to really pull out here, all measurements have some degree of error. Okay, no matter what you do, when you go from a 3D to a 2D, there's always some degree of error. Our goal is to minimize that when we are visualizing maps. So we have a horizontal datum here, and this is a reference ellipsoid and a precisely measured set of points that establish locations. So we have this ellipsoid, right, this projection, and the datum also gives us these precise points of measurement so we know where things are in relation to this shape, this ellipsoid that we're utilizing. They define a reference surface against which then all horizontal positions can be measured. A horizontal datum is determined from measurements and analysis of large survey networks. So they help us to define the shape of the Earth, which is the ellipsoid that we're using, define the location of a set of known points or control points for the position that ellipsoid is known, and it provides the reference surface and network against which all other points can be measured. So these are a few commonly used horizontal datums in North America specifically. We have NAD 27 and NAD 83. NAD 83 was meant to replace NAD 27. So every time we kind of come out with a new one, we just add the last 2 years out of that 4-digit year so that we know what's the most updated. NAD 83 is a very common horizontal datum, and it's kind of newer data. So it uses this GRS 80 ellipsoid. Remember, the ellipsoid is kind of the shape that it's utilizing to try to minimize error between that ellipsoid and then the geoid that is actually the shape of the Earth. So this here kind of shows you NAD 27. This is 25,000 measured points. This is based off of the Clark 1866 spheroid, with the fixed starting point being in Kansas. So you can see all of these measured points all around the United States. This is the 1981 version, or the Geodetic Survey of 1981. I'm just going to flip us back and forth between the two of these for a moment, okay? See how many lines? This is about 25,000 over here. See how many lines we have here. We have far more. I don't have a number on these slides, but you can just see that using this geodetic survey from 1981 and using, this is a survey network, right? So it's not just one person that went out, but more so conglomeration of multiple points over multiple places and areas in time. We have a lot more clarity as to what is where and a lot higher resolution in this map. So this is from John Porter's slides during his semester. It's just a quick joke. NAD 83, we're not in Kansas anymore. We're no longer focused on just Kansas as a central point because now we have a lot more data in NAD 83. So, datum conversions. There's a quote over here from the Geospatial Intelligence Agency. Ignoring the fine print in the margin of a map could get you killed. Sometimes you really, really need to pay attention and provide a lot of specific context and data in terms of what a map is referencing, what kind of datum it's utilizing, what kind of projection even maybe it's utilizing. If projections, coordinate systems, and datums do not match, your spatial data will not overlay correctly. Your data always seems to be off by X amount of meters. You're probably using different datums, especially if it's in the north-south direction. Maybe you're using NAD 27 and you need to use NAD 83. Or if you're using data that is very old, maybe you actually need to use NAD 27 instead of NAD 83. This is where the temporal aspect of the data that you're utilizing for your maps is very important. You need to know when that data was collected so you know what reference points make sense to compare that data to. So, be careful about mixing datums in GIS. Typically, GPS data is collecting using WGS 84. And you need to use this data for analysis along with data that uses NAD 83, let's say in this example. In that case, what is the measure of error that is acceptable for you as a user? There is no exact answer to that. You as the user actually have to make that call. So if you are looking at, let's say that you're looking at data at the resolution of a state, an entire state. About a meter probably isn't that bad. If you are looking at a plot of land, let's say it's your backyard, an error of a meter might be a big deal. So you need to be careful of that. Be careful of the datum you're using, be careful of mixing datums, and make sure that when you are specifically choosing a certain datum, you're choosing some sort of an ellipsoid that makes sense with it, as well as coordinate systems that make sense with it. So what about continental drift? Again, another thing from John Porter's slides that I just find cute. Datum adjustments are recalculations of coordinates of each benchmark. So this is why we kind of specify a reference surface. Datum adjustments help us to correct errors in distance. They help us to improve measures of that geoid and finding that best fitting ellipsoid. And it helps to also just improve computing capabilities. Typically, the better or newer something is in terms of technology, it is easier and better for us to compute. Not always, but especially in this case. I'm actually going to just quickly go over this slide. Look at NAD 27 versus NAD 83, the 86 version, the HARN version, the CORS 96 version, and then WGS 84. These are all different datums. They tell you the latitude as well as, or the longitude as well as the latitude, and they also show you how much of a shift there has been between each version or each type of datum. You can see that there's a big shift from NAD 27 to NAD 83. It is about a 36.3 meter shift. So this is going to be, let's find NAD 80 or 27 together. I guess they don't really have NAD 27 just flat on here, but you can have NAD 27 down here, right? This is NAD 27. This is where the rest of them kind of are. So you can see that is a big discrepancy between where you may tell somebody a certain location is that is of interest versus where it actually is. You can also see, though, that between the next few, the NAD 83s and the WGS 84, there's far less discrepancy. That's why when we kind of zoom in over here, we can see that, well, they're pretty similar to one another, especially our 1986. We also have our HARN, CORS 96. These are pretty close by to one another, all right? There's only about a 0.4, 0.5 degree difference between them. WGS 84, although it's still a small difference, less than a meter here, again, if you're really looking at a zoomed in, very high resolution map, looking for a very specific point, that's where maybe that about 1 meter resolution difference may be a problem. These can be fixed with recalculations. These can be fixed with adjustments of your projections, your datums and such. These aren't unfixable problems. They're just problems that you need to be aware can come up as you try to represent data on a map. So this right here is a survey control point that we actually have at the McCormick Observatory. In this figure over here, it's just showing you that there's this orange cone, and directly beneath that is one of those geodetic survey points. So it's an interesting thing that we have right here on UVA grounds. So going over to map projections now, converting 3D geographic coordinates to 2D Cartesian coordinate systems are the bread and butter. It is exactly what a projection is aimed to do. We go from the three-dimensional to the two-dimensional, and we try to represent it as best as possible. A lot of the times you're going to hear map projection, coordinate system, and spatial reference used interchangeably. This is kind of similar to when we were talking about like objects and entities and how, although they kind of mean separate things, they're spoken about in the same way. So don't let that trip you up. Esri specifically uses the geographic coordinate system and the word datum interchangeably. So when you think of coordinates, you can think of datums when it comes to anything coming from Esri. I'm going to say that one more time. Esri specifically uses geographic coordinate system and datum interchangeably as sets of words. So this is a visual of a projection, right? Projecting features onto a piece of paper here. So this is our ellipsoid, our light bulb is right there, and then this is kind of that flat piece of paper. Oh, I guess there's supposed to be a transition slide here, but I'm going to bring us back to this. I might have a slide later on in these that better shows how different projections show, and I think it's a few slides from now. But again, this is your ellipsoid. Your map is this flat object all the way on the right-hand side, and then in this case, we are projecting from the center of this ellipsoid. That's important when we start looking at different types of map projections. We have like conical ones, we have spherical ones that you'll hear about in a bit. It's important where that projection is actually taking place on the ellipsoid, whether it's the back, the center, the front, and so on. And then this is our slide. There are hundreds of map projections. Most people end up having a favorite, and the majority of us will only ever really use a few. So projections are typically categorized by projection surfaces, distortion properties, surface orientation, and again, that location of the projection of the light source. Over here, you can just see a variety of some pretty commonly used projections. We have Lambert conformal conic, we have Mollwade, we have orthographic, azimuthal equidistant, and Winkle triple. A lot of people really love Winkle triple. So they are developable, these projection surfaces. This is an example of a cylindrical projection surface and a conic projection surface, showing you where that cut line between the two of them is in the center, and then showing you, based on what that projection surface is, how it kind of lays out, what that developable surface is. So this is going to be a tongue twister for me. That developable surface is going to be basically what you have to work with to take your 3D object and lay it flat. In this case, we have a cylinder. You can see that this is an equatorial cylinder. The tangent line is right there. We have our transverse cylinder. Our tangent line is more north-south compared to the equatorial. And then I think this is a much better visual for these things. Categorizing these by the projection surface, if you see a cone, it is conic. So when you look at those projection names, if it says conic, you know that that original developable surface was from that cone shape that then got laid out flat. Cylinder is going to be cylindrical, of course, and then just a plane is going to be azimuthal. So when you think of azimuthal, you can kind of think of it of like almost looking from a bird's eye view. Over here, you see polar azimuthal as one of these projections. As somebody who does their work in the Arctic, a lot of the times I find myself using azimuthal projections because it allows me to, instead of looking at that distortion that might happen from north to south, it allows me to look directly from the north and kind of minimize that distortion. If you, though, are looking at Charlottesville, Virginia, it would not make much sense for you to use a polar azimuthal. Now discussing the location of that projection source. Gnomic means that we're at the center of the globe. Stereographic means that we're at the antipode or all the way at the back center. And then orthographic means that we have these multiple bands that are going basically through at infinity. So all of these different bands at each level kind of projecting onto this map directly. So, do projections matter? This is a link that I'm going to include for you guys instead of putting it into this video. Um, I highly recommend that you watch this because it tells you all about why projections are so important and how they actually relate to how we all see the world. I'm sure some of us, at least in this class, have heard about how different countries will show different maps. America looks bigger to us living here in America because our country, our policies, or more so our politics, that's in our best interest to show America being larger. The maps that we send out to the rest of the world, it's in our best interest politically, globally, to kind of represent ourselves as larger. However, if you've looked at maps in the past, we hear that Africa is a huge continent, right? If you kind of look at the maps that maybe you grew up with, if you have one around the house that you can take a gander at, Africa doesn't always look very large on these maps, and that's because they are based off of North America. That projection is probably based off of North America or even Europe. And they're not trying to show how massive and large this landmass is, which is Africa. Because if you think about it in terms of policy, why would you want to show how large and therefore potentially powerful a certain country or continent could be? So keep that in mind as you just kind of move around through life and you see different maps. Just notice how different continents and different countries themselves within those continents, how they're projected, whether they look large or small based on the map you're looking at. And then if you can, in the fine lines and in the kind of tangents of those maps, see where that map is from. See what country printed it, see what year it was printed. You can find some really interesting stuff. So again, I really recommend go back and look at that video. It'll be listed underneath this link. Distortion. We've talked about distortion a really good bit at this point. For distortion, we can look at principal scales, local scales, and the scale factor. Scale factors provide a measure of distortion for us. If it's greater than 1, there's an expansion distortion. If it's less than 1, there's a shrinking distortion. These are your main takeaways from this slide. Our projections can also be categorized by distortion properties. So, if we have something that is conformal, a projection that is conformal, we are trying to preserve the shape of what we're representing. An equal area or equivalent projection is trying to preserve area. An equidistant projection is trying to preserve distance and scale between things. And then azimuthal is trying to preserve direction. So again, all those names that we've been kind of listing off so far, conical and conformal and azimuthal, they do try to relay across information so that as you're kind of browsing through that projections list, you can generally whittle down pretty close to what it is you're going to end up with. So, distortion properties for shape, area, distance, and direction, right? These are kind of the four categories that we can really see some distortion in. Can a map projection preserve none of them? Most definitely. Can it preserve one or two of them? Absolutely. But can it preserve three or four of them? No. Only on a 3D object can you preserve 3 to 4 of these distortions. Or can you, I guess, more so counter these 3 or 4 distortions? So, when you preserve two properties, one always has to be direction. That's one of the things. So remember, we can preserve one or two things, but one of them always has to be direction. So then you really only have one choice as to what that other property is that you're going to preserve. Azimuthal and equidistant projections are trying to preserve for direction and distance. A stereographic projection is going to try to preserve for direction and shape. And Lambert azimuthal equal area projection tries to preserve for direction and area. The main takeaway of this slide, you don't need to memorize these things, but just kind of start to hear these words and start to somewhat associate them with what their properties are. Different projections will provide you different types of, let's say, different accuracies for different types of analysis. If I'm interested in showing you the shape of a water body, I'm probably going to go for some form of a stereographic projection. If I'm interested in telling you the area of something and differences between areas of things, I'm probably going to go for something that's about more so azimuthal. If I'm trying to tell you distance from Richmond, Virginia to DC, for example, I'm probably going to be choosing a projection that's more azimuthal equidistant. So no property can be preserved along with a property other than direction. So there's no such thing as a conformal equidistant projection, an equal area equidistant projection, or a conformal equal area projection. So I'll just kind of slide past this one. Looking at that original figure we saw about 5 or 6 slides back at this point, these variety of projections, Lambert conformal conic, Malweed, orthographic, Winkle triple, azimuthal. Your azimuthal equidistant is again trying to preserve distance and direction. So you can see there's multiple circles, there's multiple bands on that map trying to preserve the distance between things and the direction that they are to one another. Lambert conformal conic, which is a very commonly used one, is trying to preserve for that distance in the shape, or sorry, the direction and the shape. Malweed is, God knows what Malweed's trying to do. It's trying to do area. It looks like a pretty normal map, but it's direction and area. Orthographic is going to be direction and, I guess, mostly direction here, looking at an azimuthal plane almost. And then Winkle triple is kind of considered compromise. So I mentioned to you guys, a lot of people love the Winkle triple projection. And that is because it does a very decent job for most areas at still preserving most of the area, most of the distance, most of the, of course, the direction and such. But I'm going to take us back a few slides. Remember, we can always have an additional property if we want it, but direction has to be one of them. So distance, shape, and area aren't always guaranteed. We have shape, distance, and area all in these 3 different figures here. Winkle triple is just doing its best job to find some sort of compromise. But if you look at what Africa looks like, and you'll hear this a lot when people are discussing map making, the size and shape of Africa, because it is again, a huge continent. And a lot of these maps will stretch it, shrink it, distort it in a type of way, because unless you are looking at the country or the continent itself, if you're looking at a country that is around Africa or within Africa, you probably are trying to minimize the distortion in whatever area you're looking at, whether it is in the Middle East, whether it's in Southeast Asia, whether it's in South America, even. Like, they're all far enough away. The central focus point is not going to be that country, although it is one of the largest. I keep mixing up country and continent in this case, but hopefully you guys are staying with me. So, one thing I just want to point out here. Lambert conformal conic is something that you will see a lot as a projection. Winkle triple is also something that you'll see a lot as a projection. Just take a look at the country or the continent. If I mess this up one more time, I'm going to redo these whole sets of slides. Take a look at the shape and the size here, and then just come on down to the screen and look at the shape and the size here. You can see that Africa is stretched a little bit more north-south in the Winkle triple projection. You can also see that generally, as a landmass, it is larger in that Winkle triple projection than it is in the Lambert conformal conic. Now, if you look at, again, this Winkle triple projection, and you go up to the Mollwade, you can see that there's more similarity between the size of those two kind of projections, looking at Africa, than there is between both of these and azimuthal equidistant. I'm going to really hammer home this point and then move us on from this slide. Each type of projection is going to be preserving for something different. Everything has to take into account direction. With that, are you trying to preserve shape? Are you trying to preserve area? Are you trying to preserve what? It depends on what you're looking at, it depends on why you're looking at it, and it depends on the type of analysis you're trying to do. So to define a projection, this here is a Lambert conformal conic. We have an upper and a lower parallel. We have a datum. There's always a datum that needs to be associated with your projection. We have a central meridian, a projection origin, and a unit of measure. There are some standardized projections, and by that I mean the ones that certain agencies, certain governments will utilize most of the time. Projections help to preserve specific geometric properties over limited amounts of areas. The reason that we have kind of standardized projections is that it helps to impose some form of uniformity, help us with data exchange, provide some sort of quality control, and establishes limits on distortion. So you can think of it like this. This is a perfect example for some of us that might have been, gosh, I guess maybe not, but for some of us that may somehow have been at UVA as long as I have and went from the Google or Gmail kind of data organization that UVA had over to what is now Microsoft and Outlook based emails and data organization. You always want to standardize within an organization kind of like what data management you're using and how you are viewing things and where you're storing things. Because if you don't standardize it, there's a lot of confusion really quickly. Are you using Zoom? Are you using Google Meets? Are you using Gmail? Are you using Outlook? Are you using OneDrive or are you using Google Drive? Just between 2 to 3 organizations, or 2 to 3, I guess, data organization or data management facilities, there's a lot of overlap and a lot of confusion that can occur there. So, again, for those of you who haven't been around as long, UVA used to work off of Google Drive. Some of us, like myself, that came in 2021, still have Google Drive accounts. They're taking them from us now, unfortunately, but nonetheless, that transition from Google Drive over to OneDrive can potentially cause a lot of issue for standardization of things, the format of certain files and such, and the same exact thing proves to be true when it comes to a software like GIS. When you standardize certain operations, you can really diminish the amount of confusion and the amount of just general distortion that's going to happen. So, problems with using latitude and longitude. Because meridians are not parallel, the distance of 1 degree is not constant. So this kind of brings us back to that game of baseball that happened at the North Pole. This was in 1960. It was a crew of the submarine Sea Dragon, and there was a score, or they had a game based on scoring a run that required a 360-degree longitude run. And that's at the North Pole. So that's not very long around the North Pole. Again, if we were to try to do that around the equator, that might take an entire lifetime to do. So another visual over here of minimizing distortion. This is universal transverse Mercator. We have the Mercator projection. We have the transverse Mercator projection. Depending on what you're looking at depends on, or more so will adjust, which one you want to use. Are you looking at north-south, or are you looking at east-west? Do you want just the regular Mercator projection, or do you want the transverse Mercator projection? We also have UTM zones, and I'm not really going to go into depth about this, but this is just something to kind of keep in mind here. There's 60 zones, each is about 6 degrees wide. You can see that from the top to the bottom, that measure of degrees wide, there's still distortion between it. Each of those zones has a unique projection, and it's centered on its own central meridian. Coordinates are always positive. In this case, you can see here we have zone 11N. The coordinates are eastings. They're relative to an origin of 500,000 meters west of the zone central meridian, and a northing relative to the equator. All of this is kind of overkill for what you need to know. Just know there are things called UTM zones. They're based off of their own central meridians. There's 60 of them, and they're about 6 degrees wide. You'll see over here the Universal Transverse Mercator projection, which is the UTM zones for the United States. You'll see that here in Virginia, we're split between Zone 17 and Zone 18. You'll see the state of California is split between Zone 10 and 11. You'll see that over here, Texas is split between 13, 14, and 15. So this is trying its best to, again, if you think of a few slides back where we were looking at kind of projections and their surfaces and where that light may be, this universal attempt is trying to show you, okay, here are bands kind of evenly spread across the United States of America. We're not going to separate it out based on what the state is. We're not going to separate it out based on anything other than these bands are equally spaced by 6 degrees. Whatever falls within it, falls within it. So the advantages are that it's a commonly used unit, which is the meter, and it works worldwide. The disadvantages are that it is only useful at a local scale. As you saw in the last slide, it isn't good for continents. It's not even good for entire states. So unless you are looking at a specific area that is smaller than the state scale, UTM isn't going to be as helpful. It also does not align well with political boundaries, and that we could also see. There is also a state plane coordinate system to try to make up kind of for the discrepancies that we see in UTM. It was developed in the 30s. It's only used in the United States. And these zone boundaries do follow political boundaries. Not one zone crosses a state border. So this over here is using the state plane coordinate system. You can see even here, like Virginia is separated by north and south, Michigan, central and south. We also have north up here, the little scarf over the mitten. Washington is split into 3. California is split into 6. For some reason, they left Montana alone. So this is just a visual for you guys. It uses the Lambert conformal conic and transverse Mercator projection. The Lambert conformal conic is when the long dimension is east to west. The transverse Mercator is when the long dimension is north to south. So they can be mixed. It's as many zones as are needed for each state. So if I'm going to take us back here now, if you can see a certain state or a certain area, all of them seem to kind of follow through with either using transverse Mercator or not. Texas is, you can see, going from that north to south. Michigan is going from that north to south. California is abiding by north to south. But then Nevada, for example, is more so focused on east-west, as well as over here, New Mexico and Wyoming and Idaho. So just keep that in mind. If you do use a state plane coordinate system, it's going to be either based on north to south or based on east to west. And depending on which one, you're either using a Lambert conformal conic projection or a transverse Mercator projection. And this is just a visual again of where which one is being used. We have oblique Mercator happening right over here off of Alaska. This is where like Juneau, Alaska and such is. Otherwise, throughout the rest of the states, you're either using that transverse or that Lambert. And I'm going to skip us through this one because we don't really need to go too much further into our state plane coordinate systems. This is something you can come back to. It's just, again, a visual of looking at coordinate systems and their notations. So, Each map has a coordinate system in GIS. Each data layer also has a coordinate system. The map has a default coordinate system, which is typically Web Mercator. Your coordinate system can either be a geographic coordinate system, which is unprojected, or it can be a projected coordinate system. Whenever you add a new layer to the map, you need to make sure that the coordinate system of that layer that new layer is using matches the one that your map is using. Now, GIS tries to do this for you by converting them to the map projection that you are originally using if you're bringing in a new map layer. This is called projection on the fly. So over here, you'll see, by default, your map starts off with the WGS 1984 Web Mercator Auxiliary Sphere. This is the first layer that you end up with over here. However, you don't have to stay with that one. Again, if I'm looking at Alaska, if I'm looking at Barrow, Alaska specifically, this projection is probably not going to preserve much for me. If Barrow is right there, I'm probably not too interested in using, let's say, WGS 1984, or even using a fuller world projection. May not be helpful for me. There's also my data transformations, and the way that you can access this is going to your map properties tab on your map, going over to transformation, and it'll show you what your map XY coordinate system is. It'll also give you the options to transform that XY coordinate system. So you have a lot of options. You'll see NAD 1983 to WGS 1984 5, NAD 1983 to WGS 1984 1. This can get wordy, so I'll just let you take a look at this. Each of your layers, if you go right-click on layer and then properties, you can go over to the source tab and you can see what your projected coordinate system is, what your projection is. You can see where the central meridian is. From here on the spatial reference, you can understand whether or not the projections that you're using and the coordinate systems that you're using match. And if not, you can adjust accordingly. So, big picture, know your projection. All of your data is going to be created based on some coordinate system. And you may not know what it is, but it exists and it matters. So if the data comes to you lacking a coordinate system, you have to identify what the correct one is. You can't just put your hand in a hat and pull out a projection and say this is going to be the one, because that most likely is not going to work for you. So how do you find that projection? A lot of data comes with a coordinate system already assigned, luckily. But if not, check the metadata, check the .text file, check the README, check the XML files. Basically look at all of the metadata that's associated, whether it's inside of the ArcGIS Pro app or whether it's something that you need to explore a little further. Where did you download the data from? Does it have any information on that website, for example? You can also reach out to the people who created that data or uploaded that data, or people who have utilized the same data as you. At the end of the day, if you can't figure it out through those sources, trial and error is still an option for you. Assign a coordinate system, look at layers that you know have XYZ coordinate and XYZ place, and compare the two. So this over here is a .prj file. That's one of the ones mentioned looking at the projection. And you can see the information that it gives you. It gives you the geographic coordinate system, the datum, the spheroid, gives you a lot of information. So you can look for that. That's one of the easiest things you can do is just first look for that .prj file or that .txt file. Now, defining a projection, this is assigning the native projection dataset that might be missing. If you don't have a projection at all, you would define a projection. If you want to reproject, though, you have an original projection and then you want to change it, you are going to be reprojecting, so you're applying a formula that converts dataset A to dataset B, or projection A to projection B. So, reprojecting or defining a reprojection versus a projection in GIS. Each house is built at a certain address. If you forget address, you can go to the post office and they will tell you. That is like defining a projection. You're documenting something that's already there. However, if you go outside and you paint a different number on your mailbox, let's say that you're at 1234 and you put it as 145. That might not have been enough numbers there. But nonetheless, if you choose to paint over your home address, the number for your home address, and put down a new set of numbers, You have now reprojected. You've said it was originally projection A, 1, 2, 3, 4, and now it's going to be projection B, 5, 4, 3, 2. Now, if the city decides to change your address to support 911 calls, or you put your house on a trailer and you move it to a new location, that's similar to a projection because you do actually have a new address. It is actually now referenced to a different set of coordinate points or a different boundary in the case of the 911 calls. So either the frame of reference changed or the actual coordinates changed. So defining a projection is not the same as projecting. Defining a projection is just labeling it. Projecting it is actually changing or assigning the original coordinate values. Choosing a projection can be difficult. As you can see, all of these are real projections. Each one can be used for something different. Each one is helpful and useful for a different type of analysis, a different type of visualization. So this is a comic. I'll let you guys kind of flip through these because I know this is already a pretty lengthy presentation, but just a few really cute comics that'll be throughout these slides you can look at. A lot of the time, projections are going to be determined by your organization, especially if you work at something like government, right? It's less important when you're looking at very local, very regional scales, because although there is distortion, it's not going to be very much. The closer in you're looking, it's probably not as noticeable. You're not stuck with a bad choice because if you choose a projection that doesn't seem correct, you can always change it to another one. You can always reproject. And also, GIS software can help. There are projections that are organized in GIS by world, continent, and country. So always think of what is the purpose of your map. Remember this from your map design lecture. And then from there, you can utilize that so you can think of what type of map projection makes sense. If you're trying to look at a world map, right, it's a very coarse resolution. We're looking really far out. We want to try to balance shape and area distortion by using something that's a compromise. This is like that Winkle triple. This is from National Geographic. This is like using Robinson or Miller cylindrical. For other larger scale general interest maps, you may want to use azimuthal equidistant, equidistant conet, or plat carré. A conformal projection is again accurate for local shapes and angles. Topographic maps and land parcel maps will utilize a conformal projection. Navigation charts, civil engineering maps, military maps, weather maps. At scales larger than 1 to 100,000, the scale area errors are small and insignificant. They're still there. Don't be mistaken. There's always going to be some form of distortion, some kind of error, but they're not a big deal when you're using conformal as long as this is the scale, this or larger. So remember, small scale, large area, large scale, small area. If we're looking at equal area, this is an area on map in proportion to area on Earth. The spatial extent of a categorical attribute is important to you in this case, the density of an attribute with dots, or quantitative attributes by area. So if you're looking at something like GDP, you may want to use equal area. If you're looking at land use maps or population density, you may want to use equal area. Now, if distance is what's important, getting an accurate distance from some given point. This is something like maps of airline distances from one city to several other cities, right? You want to kind of have an idea of how actually far things are. These are going to be things like your seismic maps. These are going to be things like maps used to calculate cost based on distance from one another, and also to calculate like ranges, habitat range of an animal species, cruising range for an airplane and such. And then direction, accurate direction from a given point, probably azimuthal. This is great for navigation and route planning. Maps purpose narrows choices, but you still need to make a decision, right? There is a time-honored rule dating back to the 16th century to choose according to the latitude of your area of interest. If you're looking at a polar region, you're probably going to want to use azimuthal. If you're looking at kind of a middle latitude, you're going to want to use conic. And if you're looking at a tropical region, you're probably going to want to use cylindrical. This is a rule of thumb, but it's not something that you have to follow. Just something to keep in mind that this is how a lot of people have chosen their projections based on their area of interest. So, Polar, planar, tropic, cylindrical, you can see, middle, conic. You can kind of see why they may choose this. Over here, the center of the dot for planar, or azimuthal, kind of lines up. There doesn't seem to be too much distortion. For middle portions or middle latitudes, conic, that's kind of like our Tropic of Cancer, Tropic of Capricorn. There's still going to be less distortion. And then for the true tropics, cylindrical, we're minimizing distortion there as well. So this is kind of where that rule of thumb comes from. This I'll let you come back to if you ever want to look at it. I would suggest maybe screenshotting it. I'm not sure where my face shows up for you guys on these slides, but I'll move myself temporarily. So screenshot this. It's just a nice thing to know of where there is minimal and moderate distortion between different things. Between like the very first, or let's say the second one is Albert's equal area conic. It'll tell you what the properties are, what the suitable extents are, what the suitable orientation and latitude is for all these different projections and what they can kind of provide for you. This is another, this is one is focusing more on the Mercator projection in this case. It's telling you we preserve shape and show lines of constant direction. Although it's often used as a reference map of the world, it's not very well suited to its purpose apparently. So again, I suggest you just kind of screenshot these, keep them on your desktop somewhere if there's something useful to you. Another cute comic, projections according to the xkcd.com webcomic. I won't go over it, but I'll let you guys come back to this if you'd like. This is a visual of the Mercator projection and where that distortion occurs. You could see in further north and further south, there's a lot more projection, but kind of towards the center, especially towards the tropics and those areas towards the equator, not quite as much. This is Robinson. You can see it's kind of an attempt at being that compromise. This is equidistant cylindrical. You see that that distortion is more north-south, but doesn't seem to be as much east-west. This is Cordic Alphalic. I have never used this projection before, but I'm sure somebody has. You can see, though, that it is pretty great for Central America. It's pretty great for the central portion of Africa, some regions of Southeast Asia. So just a thing to keep in mind. I haven't used it. You might use it. Good homolocene. It's an interrupted projection. This is one of the best visuals of that orange peel example. Taking that 3D orange peel and trying to flatten it out. This is realistically what it might look like. And then, this is from one of John Porter's slides. I'm going to skip past it. I don't feel like talking about this man right now. This is one of his projections, though. This is the Bond projection. Looks like a heart. This is an old Mercator projection from way, way back. You saw this many slides ago now at this point. Ooh, I'm not trying to change me. This is an equidistant conic. This is another equidistant conic. These are using different central meridians. So you can see just between those two slides how that shifts. Another set of comics here, and then kind of summarizing our map projections, okay? Projections are meant to specify two-dimensional coordinate systems from a three-dimensional globe. Any projection that you choose, no matter what it is, will cause some type of distortion. You can limit this distortion and the errors that come from it by intentionally choosing your projection for whatever it is that you are looking at and trying to visualize. We have some standardized projections at different organizations, different agencies, and your projections differ by datum, so know what your parameters are. Use of your knowledge of projections is only meant to be used for good and not for evil. If you go back and look at the link that was kind of in the middle, mentioned in the middle of these slides, again, we'll post that actual link for you underneath this set of slides. You'll be able to see, again, how, especially in things like government and policy, politics, you can utilize your understanding of distortion to intentionally distort somebody's idea of what's real and what's fake. How large a certain country or a certain continent may be compared to the countries or continents nearby it. So you've learned about ellipsoids and their relations to geoids. You've learned about datums and why they matter. You've also learned how to project onto a curved surface, onto a flat surface, and the general rules for how to go between those. In ArcGIS, you know the difference between defining a projection as well as actually projecting data. Labeling data versus changing coordinates. Think of it again as You have a number on your house outside. If you paint over it with a new set of numbers, the original numbers are the labeling. The painted over of numbers is your change in coordinates. So with that, you've made it through the end of the slides. Um, I know that these are a longer set of slides, so maybe I should have said this at the beginning. I'll probably label it on this link for these. I might suggest splitting this up over 2 to 3 days. It's a lot of information. It's a bit more in depth on this information as well. But once you've gotten through these slides, go ahead and do tutorials for chapter 3, your assignment for chapter 3. Be sure to go on to Piazza and ask any questions. A good thing to keep in mind is that Piazza doesn't only have to be for the tutorial assignments or the actual assignments. You can also ask questions based on the lectures. Because this is an asynchronous course, there isn't the opportunity to stop, ask questions, raise your hands during the class. So I would highly suggest if you're kind of struggling with coming up with a Piazza question, then utilize something from the slides that you're looking at. It's a really good way to get clarification on topics and also start conversation. So with that, good luck with your tutorials, assignments, and Piazza, and I will see you guys over at lecture 4.